so I don't really need to go over anything else, right? I'm sure. All right. So we've talked about span. Remember, span was our set of all linear combinations of a certain set of vectors. That's when we have span a set. We started talking about linearly independent sets last time. I guess it's been almost 2 weeks now. We could go last Wednesday, where we said that. Where did you do that? Yeah, make it nice so it's not all lined up. Wait, great. So we said that the definition of linear independence is that if we have a set of vectors v1 to dn, we say that set's a linear independent set if the only linear combination that gives you the zero vector is using all zeros for your constants. We know that there is always a linear combination that will give us a zero vector because we know that if we multiply a vector by the scalar 0, we'll get the zero vector. It was actually on your exam to prove, right? Okay. So we know that we take zeros for all the scalars. We will get the zero vector as a linear combination. For linear independence, we want that to be the only possibility, right? Okay. So we did a couple of examples last time. We asked if that particular set of vectors is linear independent. We just picked out one of the examples out of the book and looked at the set of 3 vectors and asked if it's linear independent. We set up a system of equations. We know that to solve the system of equations, we row reduce, and we notice that basically the matrix that we're getting to row reduce, we can just write those vectors as columns in the matrix and then row reduce and get what we need. We did that same thing for matrices in the next example, and noticed again that essentially we take these vectors, write them down as columns in your matrix, and row reduce to see what you get. In order for it to be linear independent, remember we want a unique solution, right? We want the zero vector, the solution that has only zeros to be the only solution, right? So we want no free variables when we row reduce, so we need a pivot in every column. Is what we're looking for. For spanning, what did we need to see? A pivot in every row. We want to know that a solution always existed, right? The reason why we care about linear independence, and that was the last thing we basically talked about before we started doing some different properties, the reason why we care about linear independence is that if I can express a vector as a linear combination of the vectors in my set, then that's the only way to do it. There's only one way, right? The unique representation, which allows us to talk about coordinates. And you've dealt with coordinates ever since you started dealing with graphing, right? So that's one of the reasons why we care about linear independence is that uniqueness property. If there is a linear combination that gives us that vector, it's the only linear combination that does. All right. So we talked about that any set that has the zero vector in it must be linearly dependent. And again, that's because I can use any constant here out in front of the zero vector. It's not just the zero constants. All right, so let's talk about some of these other properties. And this is why we use the dependent name. It's this particular result. If we have a set with at least 2 vectors in it, that set is linearly dependent if and only if at least one of the vectors is expressible as a linear combination of the others. So remember, we have an if and only if statement. We actually have 2 things to prove, right? I got to use the if the first part, then the second part, and vice versa, right? Okay. So a lot of times, at least when I'm writing the different things, I'll use a double-headed or a double-barred arrow to talk about which way I'm trying to prove. So when I write it from this way, that means that I'm assuming that the set is linearly dependent, and then when I show that one of the vectors is expressible as the others, and then I'll write the other arrow going the other way to prove it the other way. All right. So let's suppose in this direction that S is linearly, bless you, dependent. Linear independence means if I have a linear combination that gives me the zero vector, then all the constants have to be zero. So if it's linearly dependent, that means there exists a linear combination of the zero vector where not all of the constants are zero. That's what it means to be a linearly dependent, right? Okay, so if it's linearly dependent, then I guess I didn't say what the set S is. Let's just assume, I'm going to assume for argument's sake that my set S is V1, V2 out to Vn. So if it's linearly dependent, there exist scalars, not all zero, such that C1, V1, C2, V2, out to Cn, Vn equals a zero vector. So again, I'm trying to emphasize this point. When we're talking about linear independence or linear dependence, we're talking about a linear combination that gives us the zero vector. That's what that definition involves. Linear independence says that if you have a linear combination that gives you the zero vector, then the constants are all zero. So if it's linearly dependent, there must be at least one linear combination where not all of the constants are zero. Okay? So that's all I'm saying here. This is just definition of linear dependence, or equivalent to the linear independent definition. All right, so we're trying to show that at least one of the vectors is expressible as a linear combination of the others. And that is exactly what linear dependent means, right? One of the vectors depends on the rest. That's the idea, right? I can write one of the vectors as an equation involving the others. Okay. All right. I want to show that at least one of the vectors is expressible as a linear combination. This statement here says at least one of these constants is not zero. So which vector do you think I might want to try to write as a linear combination of the others? Well, let's say Cn is the one that's not zero. What one you want to try to write as a linear combination of the others? And let's think about why it needs to be important, and that it's a constant is. Let's think about why it has to be important that the constant is not zero. Oh, yeah, exactly right. So if you had something like, say, 3x plus 4y minus 5z equals the zero vector, say, what would I need to do to solve that for z? Yeah, do the 5z over and divide by the 5, right? This is why it's important that at least one of the constants is not zero, so I can divide by it, right? If I want to solve for that variable, as I think about it as a variable, if I want to solve for that vector, I need to be able to divide that constant off. In order to be able to divide the constant off, I need to know that it's not zero. So if we have linear dependence, then one of those has to be not zero. So that's the thing that I'm going to solve for. Okay? So let's just say, this is math speak for it, the number doesn't matter. Without loss of generality, let's assume that Cn is not equal to zero. One of them has to be not zero. At least one of them has to be not zero. So I'm going to assume that Cn isn't. If Cn happened to be zero, then reorder your vectors. Just rename them. That's what without loss of generality means in math, is that I've named them V1 out of Vn, but it really doesn't matter which one's the first one, which one's the second one, and so on. So I'm arbitrarily saying the last one has the non-zero constant. All right, so now I can solve for Vn just like I solved for Z here, right? You'll have negative Cn Vn equals C1 V1 plus C2 V2 plus Cn minus 1 Vn minus 1, or Vn is equal to negative C1 over Cn V1. Guess that's a minus now. All the way out to Cn minus 1 over Cn Vn minus 1. Do we now write one of the vectors in terms as a linear combination of the other? Yeah. So this is exactly what we wanted to prove, right? For that direction. Okay. And again, this hopefully illustrates why we use the phrase linearly dependent. The Vn depends on the other vectors. Notice that we can do the proof in the other direction as well. If we assume that we have one of the vectors as a linear combination of the others, basically I just work backwards and get a linear combination of a zero vector that's not all zeros. In particular, if I just replace these with other constants here, this constant would be a 1 for certain, and then you could just move everything over to the other side, and now you have a linear combination of the zero vector where not all the constants are zero. So the other direction is just a straight, basically it's doing this in reverse. So that's a good practice to see if you can write out the proof going the other direction. Notice that C, part C here in our theorem, is essentially part B. It's just a negation of everything, right? The negation of linear dependent is linearly independent. At least the negation of at least one vector is no vector. So it says part C says the exact same thing as part B does, just in terms of linear independence versus linear dependence. All right, so again, the moral of the story with these two things is, if we have a linearly independent set, then one of the vectors cannot depend on the others. Does that make sense? All right, cool. Notice the last part here is just saying if you have exactly two vectors, well, the previous theorem said that if it's linearly dependent, then I can write one of the vectors as a linear combination of the others. Well, there's only one other vector, right? So if it's linearly dependent and has two vectors, then one of them has to be a scalar multiple of the other. So if it's linearly independent, then neither is a multiple of the other. So this is just a special case. And the special cases basically helps if you can look at a set and say one vector is 3 times the other, then I know it's linearly dependent. All right. So why do we care? That's the important part, is why we care. We're getting there. All right, so let's look at this next theorem that we have on the next page. We've got a set of vectors in Rn, and it says that if k is bigger than n, then S must be linearly dependent. Now let's think about this before we try to prove this, because we're actually going to do the proof more generally, so that it'll work for other vector spaces besides Rn. But remember when we talked about how we can look to see if a set is linearly dependent or not. We took the vectors, made columns in a matrix, and row reduced, right? Okay. if all my vectors are coming from Rn, how many rows and how many columns is that matrix going to have that we form? Remember, the idea was to take the vectors and make columns, right? So how many rows and how many columns are there going to be in that matrix? There'll be k columns because there's k vectors, right? How many rows? N, right? Because each one's coming from Rn, correct? Because there'll be n components. So you'll have an n by k matrix, right? The n rows, k columns. Which one's bigger, number of rows or number of columns? If we'll by this assumption here, which is bigger? The number of columns, right? So if you put this in reduced row echelon form, and you definitely have more columns, what's going to happen when you do find the reduced row echelon form? In every column, good. Guaranteed not to have a pivot in every column, right? There's too many, right? Remember, your pivots have to go down to the right. I'm going to run out of rows before I run out of columns, right? So you're guaranteed to get pivotless columns, which means that you're guaranteed the set will not be linearly independent. Again, so we can think about that specific idea in Rn, right? When you create that n by k matrix and row reduce, you're going to run out of pivots. You're going to run out of columns for pivots, or run out of rows for pivots until you hit every column. Notice you can do the same thing for span, right? If it's the other way around. For spanning, you need a pivot in every row, right? So if you flipped your k and your n around, if k was less than n, there's no way to be able to span. All right, so let's see if we can prove this theorem more generally. I want to show that this is linearly dependent, and the idea here is to come up with a system of linear equations where we're going to get more rows than columns. Okay? All right. So if we assume that it's linearly independent, well, let's see if we can set up a system of equations here that give us the zero vector. Pardon me. Goodness gracious. So let's see if we can create up our system of equations like we just talked about. So we want to, again, consider a linear combination that gives us the zero vector, right? So we write it out a little bit more formally. And again, it's this idea of being able to make those columns. It's the C's that we're trying to solve for here, right? Those are the constants that we're interested in. If it's going to be linearly dependent, then we need to come up with a homogeneous system that has infinitely many solutions. That's the idea. All right. So since we know that these are all vectors in Rn, I know that my V1 is going to have some components to it, or V2 will have some components to it all the way down, right? Okay. And then we'll have to equate first components, equate second components, and all the way across, right? So let's say I have my C1. Let's say the first component here is, let's just call it A11. So this will be the first vector in the first component. Oops. And then I'll call this one A12. So this is the second vector first component. And so on down the line. This equates first components. We'll have another one that equates second components. And so on down the line. Oops, this should be a C1 here, sorry. So this is our system of linear equations that we need to solve. And this looks a lot like when we were talking about our process, right? So if I've got a linear combination of these vectors that gives me the zero vector in Rn, then the first components have to, whoops, those shouldn't be zero vectors. Those should just be zero on the right-hand side. Sorry about that. Got a little vector happy there. Then my first components, when I put them together, have to equal 0. My second components have to equal 0. All the way down to the nth components have to equal 0. That's what we just said, right? All right, so notice that I'm using the fact that I can write my v's as components. So my v1 has components 1, 2, out to n. First component, second component, nth component, right? Associated with the first vector. My second vector has components, first component, second component, and so on down the line. All right, so the first component, the first subscript of my A's is referring to what component you're in. The second subscript is talking about what vector you're in, right? So the A11, A21 out of AN1 are the components for V1. A21, 1, 2, 2, 2 out to N2 are the components for the V2 and so on down the line. And now we see, hopefully, our homogeneous system. What did we say we were trying to solve for? The A's or the C's? The C's, right? So I can make my coefficient matrix this way. That was our coefficient matrix, isn't it? What size matrix is that? You just told me a little bit ago. What size matrix is that? Is n by k, right? It's associated with a homogeneous system where we've got more variables than we have equations, correct? So what's going to happen when you row reduce this? You're getting pivotless columns. That's exactly right. They're good columns that don't have pivots in them, which means you're going to get free variables, which means you get infinitely many solutions, right? So just to write this out, this homogeneous system has fewer equations than unknowns, so it has infinitely many solutions. Therefore, S is linearly dependent. Because again, the only solution must be all zeros if it's going to be linearly independent. All right. Okay, so let's see if we can look at some examples here. Get some things with numbers in them. Hopefully these examples won't be too difficult to see what's going on. It should illustrate what we've just been talking about. Except that should be a comma behind that 1 in the second vector there. That's the first example. What's wrong? And why can't the first? By the way, none of these are linearly independent. They're all linearly dependent. What's wrong with the first set? It has the zero vector in it, right? In the first one, this is linearly dependent because the zero vector is in it. Okay, right here. The zero vector is in S, so S is linearly dependent. You don't have to do any other work. Okay? Period. If the zero vector is in there, it's linearly dependent, you're done. Okay? What's wrong with the second set? The second set goes back to the theorem we just proved. How many vectors are in the set? 3. What are they all vectors in? R2. The number of vectors is bigger than the number of components, right? Okay. So for this one, it's linearly, the K here is 3, your N is 2. That's what illustrates that previous theorem, right? More vectors than components. So it's linearly dependent. Yeah. You don't have to apologize for asking a question. You can always ask a question.
S is always like a sample of D, right?
It's always a subset, yeah.
So do we assume that the zero vector is always zeros?
The zero vector for R3 is all zeros, yes. Or any of the RNs. For P2, it'll be the zero polynomial. For the matrices, it'll be the matrix that has all zero entries. For our standard ones, it should be all. It should be what you think of as zero every time. Yep, you're welcome. What's wrong with the last one? The last one goes back to the previous theorem we talked about. Is it? So I don't think I want to try to use quadratic things. But what do I notice about it?
The second vector is a factor, or I guess a multiple of the first.
Yeah, so notice that if I multiply the first one by 2, I get the second one, don't I? So I have one of the vectors as a scalar multiple of the other. Actually, scalar multiples of each other, right? So the 6 minus 4x plus 2x squared is 2 times the 3 minus 2x plus x squared. So again, that's just when you have a set of 2 vectors, that's a quick check to see if it's linearly dependent or not. If you can find a scalar where one of them is that scalar times the other, then it's linearly dependent. Any questions on those examples at all? Does that make sense what we're doing? All right. This one hopefully ties into other stuff that we've been doing. These exercise numbers don't correspond to our book. These correspond to the book I was using when I made up this handout. So you can ignore the exercise numbers. This one asks, what values of lambda make a linearly dependent set in R3? What do you think we might want to do with this one? Think about it this way. Anytime I give you a set of vectors and ask you if it's linearly independent or not, what do you think you're going to form? A matrix? How are you going to form your matrix? Each vector is a column. Good. Yep, that's exactly right. So let's do that first. Say that again. It would, yeah. The matrix is symmetric, so it wouldn't matter if it was rows or columns, but generally speaking, it matters. I don't want to think of it as columns. Now, every other time we've done this, we've row reduced, right? But it's a little harder to row reduce when we've got variables in it, because then I have to worry about if the variables are 0 or not and all that good stuff. But there's another way to check whether or not this matrix has a pivot in every column when we row reduce. Notice this one's square. A pivot in every column in this case also means a pivot in every row, which means your reduced row echelon form becomes what matrix? The identity if it's going to have a pivot in every column and row, right? We know that being row equivalent to the identity is equivalent to being invertible. What numeric check is also equivalent to being invertible? What's not zero? The determinant is not zero, right? Yeah, that's the numeric check that we have, isn't it? So I can also check to see if this is linearly dependent or not by doing what, do you think? Take the determinant and set it equal to 0. Yeah, right? If the determinant is 0, that also makes it linearly dependent in this case, right? So if we do the determinant here, bless you. I'll expand along the first column. So I'd have lambda times lambda 1, 1 lambda, minus 1 times 1, 1, 1 lambda, plus 1 times, oops, yeah, that's right. And then so eliminate that row, 1, 1, 1 lambda, eliminate that row, I get 1, 1 lambda 1. Make sure I have the right things written in there. So do each of those determinants. You get lambda times lambda squared minus 1 for the first one. And then I've got lambda minus 1 for the second one, but that'll be minus for that coefficient out in front of the 1. And the other one will be 1 minus lambda, right? I'm going to need to factor this if I want to set it equal to 0. Notice that there is a factor of lambda minus 1 in each of these things already. So if I factor that out, it'll make my life a little bit easier to start with. In the first one, we'll get left with a lambda and a lambda plus 1. This will be minus 1. This is also a minus 1 when we factor out lambda minus 1 because the signs are reversed, aren't they? So we got a lambda squared plus lambda minus 2 in that second factor. And that factors as lambda plus 2 and lambda minus 1. So we got a lambda minus 1 squared and a lambda plus 2. What makes that determinant going to be 0 then? What will make the determinant 0? 1 and negative 2? Right? And if the determinant is 0, what does that say about the original set of vectors? Well, let's do it a little bit faster. Or not faster, slower. If I make each of these, make the determinant 0, what does that tell you about this matrix? If the determinant is 0, what does it tell you about the matrix? It's singular, right? So the matrix is singular. If it's singular, what does it tell you about the reduced row echelon form? Can it be the identity? If it's singular, no. So that means when you row reduce it, you'll have a pivotless column. And if you have a pivotless column, what does that tell you about the set? It's dependent. Good, exactly right. So this determinant is 0. When lambda is 1 or negative 2, which means the set lambda 1, 1, 1 lambda 1, 1, 1 lambda is linearly dependent when lambda is 1 or negative 2. So notice that the principle was the same that we've been talking about. If I want to check that something is linearly independent or not, we took the vectors and we made a matrix by taking those vectors and making them the columns. But rather than row reducing in this case, because it's a little bit trickier when we've got variables involved. Because if you row reduce with things with variables involved, when you start dividing by things with variables in them, you have to make sure those variables aren't 0, right? It was a little bit easier here to do determinants and talk about whether or not it was invertible through determinants, and then that told us whether or not we would have pivotless columns or not. Does that make sense? So if you get a question like this where it asks you to find values for the variable that make it linearly dependent, set it up the same way, but work with it from a determinant angle rather than trying to row it. So we're starting it in the exact same way. All right. Let's look at the next one here. We have a linearly dependent set of vectors to start with. Then if we start adding to it, it stays linearly dependent. That's what this problem says. Okay, so if you already have a linearly dependent set of vectors and you throw more in it, it's still linearly dependent. Now, why would that be the case? Again, if the original set is linearly dependent, what does that tell you? So that's a way for Rn to tell us that, right? If I've got more columns than rows, and I'm guaranteed that it's linearly dependent. So if I think about these as vectors in Rn, we can think of it that way, right? I would have more columns than we have rows. So if I throw more vectors in there, I would still have even more columns, right? So it didn't get any better, it got worse. Okay. But when I try to do this more generally for things that aren't necessarily vectors in Rn. So what does it mean for linearly dependent again? What's our definition? Okay, so that's one of the equivalent conditions for being linearly dependent is that one of the vectors is a linear combination of the others. Okay, let's see if we can work with that. Let's say your VK is C1 V1 plus C2 V2 out to CK minus 1 VK minus 1. That's one of our equivalent conditions for being linearly dependent is that one of the vectors is a linear combination of the others. This is that without loss of generality again. I said, let's say the VK is the one I can write in terms of the others, right? The subscripts are kind of arbitrary here. The ordering is arbitrary. That's all without loss of generality means, by the way, is if I pick some arbitrary order that doesn't really matter, I might as well just have said the last one is the one I can write in terms of the others. All right. Now that I have VK as a linear combination of the V1 out to VK minus 1, can I write VK in terms of the bigger set? What can I use for the constants for all the other vectors? Devin just told me a second ago. I saw you do the hand motion. What can you do? Zero. Yeah, make them all zeros, right? If I can write VK in terms of the V1 to VK minus 1, then I can certainly do it for any other vectors on the end. I can just start doing 0 times it. So now I have one of the vectors in the set written as a linear combination of the others. Which is what we needed. I know it still feels like cheating, but remember that for linear dependence, we just need one non-zero constant to give us that the zero vector for the linear for it not being linearly independent. So I can use zeros everywhere else that I want. So if I know that I can write the VK as a linear combination of the first K minus 1 vectors, then I can tag on as many as I want on the end by using zeros. It doesn't change anything. That's the idea. So it stays linearly independent. And that's the same idea that we just mentioned before, that if they're vectors in Rn, all we've done is just add more columns. We can't get pivots by adding columns. Right? We already ran out of rows to get pivots in. If we start adding more columns, we can't get any more pivots. Does that make sense? Okay. This last one is a special case of doing things with doing functions that we can do derivatives of. So this one actually requires more work, and we'll talk about this in section 4.8, assuming we have time to do this. You do this in differential equations, by the way, if you want to check that a thing is a set of functions is linearly independent by doing a determinant calculation. So we'll talk about that in section 4.8 if we have time. I want to go on to talking about new stuff today anyway. So don't worry about this one right now. We'll come back to it if we have time. And if you take differential equations, you'll definitely do it. All right. In any event, any questions on linear independence? We're going to expand on this idea here. All right. So let me give you another handout that goes along with what we've talked about. So we talked about spanning sets, and we've talked about linear independent sets. So now we're going to talk about putting those two ideas together. All right. There it is. All right. So let's talk about why it's easy to check that this set is linearly independent in span. If I want to check linear independence or I want to check span, what do you do with the vectors? So before we redo this, we make a matrix, right? How do you form a matrix again? Yeah, make vectors as columns, right? What matrix are you going to get when you put in those vectors as columns? It'll be the identity matrix, right? Why is it linearly independent then? Why is the set linearly independent? Yeah, there's a pivot in every column, right? Why does it span? Pivot in every row, right? So when you form your matrix, you get the identity matrix here. So make those vectors as columns, row reduce it. Okay, poof, I row reduced it, right? Okay, so the set is linearly independent because there's a pivot in every column. And it spans because there's a pivot in every row. Okay, that makes sense? That's same stuff we've been talking about, right? So it's linearly independent and it spans. Let's think about why that might be a big deal before we do the next one. Remember that span is existence. We can write every vector in R3 as a linear combination of these three vectors. Linear independence is uniqueness. All the linear combinations that we form are unique linear combinations. If I change the combination, I change the vector. So putting those two ideas together says that I can express every vector in R3 uniquely as a linear combination of these three vectors. And you do this in Calc 3, you do this in physics, when you write things as something times I plus something times j plus something times k. Right? You do that in those classes. And you use that idea. Because I know that I can express every vector in their coordinates as a multiple of the x direction, a multiple of the y direction, a multiple of the z direction. The z direction. That's z direction, up and down, right? X, y, z, right? Okay. Landing a plane at this point, or conducting an orchestra, one of the two. All right, let's do the next one. We want to show that this is linear independent and it spans. Well, again, if I'm doing P2, remember P2 looks like second degree or less polynomials, right? So again, how did we check to see if something was linear independent or spans for P2? What did we do? Well, we did it for R3. We did it for matrices. What do we do it for polynomials, do you think? You can still put it in a matrix, right? Because I can think of these basically as coordinates, right? What matrix would we get out of this? What column do you think we would form from the 1? Yeah. 1 is 1 plus 0x plus 0x squared, right? So I would do 1, 0, 0 here. What do you do for the x? Yeah, 0, 1, 0. What would you do for the x squared? 0, 0, 1. Hey, that looks the same, doesn't it? Do we get a pivot in every row? Yep, so it spans. Do we get a pivot in every column? Yeah, so it's linearly independent. Notice again that we're using the idea here. If you were trying to form your... Go away. Stop. Why are you doing that? You're doing the idea here that 1 is this... if you're doing a linear combination here... that gives you the 0 vector. Then I can, if I'm thinking about my polynomials here, I can think about this as 1 plus 0x plus 0x squared, and likewise down the line. So we're getting the equation C1 equals 0, C2 equals 0, and C3 equals 0. We're forming that system of that homogeneous system again, right? Thinking about A, B, C. Does that make sense? Writing it that way? Okay. All right. Again, this tells me that I can write every single thing in P2 as a linear combination of 1x and x squared, which makes sense because isn't that how you write second degree polynomials? As something times the x squared plus something times the x plus a constant term? Isn't that exactly how you write a second degree polynomial? At least I hope so. All right, so this leads us to the definition of basis, and then we'll play more around with this on Wednesday. If we have a non-empty set, well, actually, technically there is one vector space that has an empty basis, but we'll talk about that. That's a special case. We say that S is a basis for B if 1, S is linearly independent, and 2, S spans V. A basis is a linearly independent spanning set for the vector space. And again, the reason why we care is because that guarantees that we can write every single vector in the vector space uniquely as a linear combination. Right? It's that uniqueness bit that we want to. All right, so we'll do more examples of this next time. Talk about basis, talk about dimension, and all that good stuff. Have a good one. See you on Wednesday. You know, I realized I wrote on your homework that your homework is due on Friday. That's a little hard to do since we don't have class on Friday. I forgot about Good Friday week on Friday. So change that to Monday because I'm not going to make you turn it on Good Friday, obviously. Sorry about that. I put that on there this morning and forgot. We don't have class, right? All right. Have a good one, everybody.